Hi guys, and welcome to another video in the HSC Chemistry series, this one from the acidic environment. And we're going to focus on using the pH scale. The pH scale is something that we talked about right from the beginning of this topic when we were looking at indicators and their uses. And it's a very convenient type of a scale because it allows us to plot a range of different acidic, neutral and basic solutions on a logarithmic scale. A few important things just to, I guess, set the context for this video. Firstly, one very important equation, which is always on your data sheet. So this will be part of any exam that you sit, both an internal exam for part of your assessment tasks and also for your HSC. This formula will be given to you. So you just need to make sure you know how to use it. The concentration of the H+ ions, which is equivalent, we now know, to the concentration of the hydronium ion, should be expressed in moles per litre, and then it can be converted directly into a pH value. Any change in 1 unit on the pH scale is going to correspond to a 10-fold change in the concentration of the H+ ions, and that is simply because of the log base 10 of this particular expression. Sorry for the phone. Acid solutions then have a pH that is less than 7, where the delta H value is greater than 10 to the minus 7. Neutral solutions, we know that water ionizes into H+ ions and OH- ions, and each of those has a concentration of 10 to the minus 7, and hence the pH of neutral solutions is 7. And then anything that has a lower concentration of hydrogen ions, less than 10 to the minus 7, is going to have a pH that's above 7. So the important thing to remember about this particular formula is if pH is equal to minus the log base 10 of the concentration of H+ ions, we can convert this into a concentration of H+ ions where we raise 10 to the power of the negative pH. So that's just rearranging this equation here, and I'll walk you through that if you need me to do so. But it's just an easy way of being able to convert from pH to concentration of H+ ions, or from the concentration of H+ ions to the pH. And these are the types of solutions that we find. So a quick example then to walk us through. 20 mils of a 0.08 molar hydrochloric acid solution mixed with 30 mils of a 0.05 molar sodium hydroxide solution, and we need to find out the pH of the resultant solution. So the important thing when you're working through these particular examples is you first of all need to make sure that you have a balanced equation. And the balanced equation is only important in this case because we're interested in the mole ratios, NaCl, aqueous, and H2O. And this is balanced, so therefore our mole ratios are 1 to 1 to 1 to 1. Now, we also need the very important formulas. N is equal to CV, or C is equal to N on V. Same formula, just rearranged. And these will help us with our calculations. So, for example, when we are looking at C and V, we have a concentration for the hydrochloric acid of 0.08 and a volume of 20 mils, which is 0.02 litres. And so working on N equals CV, we have a number of moles of 0.0016. For the sodium hydroxide, the concentration is 0.05, and we have a volume of 0.03. So working this one up, we have 0.0015 as our number of moles. Now, because the ratio is 1 to 1, the key thing with this particular example is that we don't have exactly the same number of moles of each, and so therefore we will have an excess. The excess in this case is going to be the greater one, which is the excess HCl, and that will be found by subtracting what we have of the hydrochloric acid, and then what we have, and then subtracting the number of moles of sodium hydroxide for the neutralization. So we will have 0.000 0.01 moles. Now, the only problem with this particular one is this is our number of moles. This is not our final concentration. So in order to get our final concentration, we have to look at the value that we have for the concentration. A concentration is number of moles over volume. Now, because we added 20 mils, I'm going to just pop this down in a slightly different color. 20 mils was added to 30 mils. Our final volume is 50 mils. So we have 0.0001 on 0.05. Now I'm just going to quickly do that calculation for you. So I've got a value of 0.002. Now that's the concentration. So therefore, what I will need to do, I'm just going to move this into a slightly different color. pH is equal to minus the log of the concentration of H plus ions. And so therefore we want minus the log of 0.002. And that is going to give me a value of 2.70. 2.70 will be my pH of the resultant solution. Just as a quick aside here, important to realize that water itself is a substance that is capable of self-ionizing. So if you'd like to consider it this way, we can have one water molecule acting as an acid and one acting as a base, and therefore there's going to be a donation of a proton from one to the other. That's going to give us a hydronium ion and an OH ion left behind. When we look at this equation, we know that because the pH of water is 7, therefore the concentration of the H plus ions must be equal to 10 to the minus 7. And of course, because the ratio is 1 to 1, the concentration of OH minus ions must be the same. We can use the calculation for pH to also give us a pOH if we know what the concentration of the OH minus ions is. And in fact, when we multiply these together, we get a constant, a value of the equilibrium constant for water, because this is a situation which is in equilibrium. So that produces a resultant, very important result, that the pH plus a pOH is equal to 14. And this is going to be very important because sometimes we're going to be looking for the pH of, say, a sodium hydroxide solution, where we can't directly calculate the concentration of H plus ions, but we can calculate the OH minus ions. And we'll do some examples of this in class. Thanks for watching.